Okay, good morning. Let's begin our lecture. So first of all, I would like to know if you have any questions. And while some of you might be still typing your questions, I do have a couple of tips I would like to give you. So mostly grading your work, all of your work is graded by the TAs. If you have any type of issues or you do not understand your grade, generally you can see what problem you missed your points on. In the rubric, it will have like a specific comment, and generally it also has a name of a TA who actually graded this problem, so you can directly email that TA. All the TA's emails, I believe, can be found on the syllabi. Now, the other thing I want to mention is today you're going to have discussion 5. I do believe that groups might change every discussion depending on who shows up and who doesn't show up, or sometimes you just didn't like to work in the group you worked before, or sometimes you had to miss and you need to do the online discussion section or something like that. So due to that, every single discussion, you have to create a new group, which always has a discussion number. So if you go to people's, you're going to have like option for discussion 2, 3, 4, and today you have a new group for the discussion 5. Please make sure to join the correct discussion because it makes things so much easier. For grading and everything, and especially for people to be able to see the okay. Now another thing, I did had a couple of not complaints, but for some of you, quiz finished up before you push the submit button, and then it sometimes doesn't. Well, most of the times it doesn't really save the things you typed in. So please make sure after you submit quiz or submit work, including like discussions and everything, don't just push submit, go away and forget about it until you see the grade. Directly after you push submit, go to your submission and check everything is submitted correctly. Because if it didn't submit it correctly, a week after, I will not be able to change anything because I don't know when the things were done or anything. I cannot help. However, if you pushed on submit button on the quiz or the quiz went like bad, and then you're checking and you're missing directly after it, you're missing the question, what you can do is you can always email me directly with the solution or the like picture of the solution, some type of a proof you just did it in the next like 10 minutes. And then I can see, yes, you really did it. There was a technology issue, and this is like, I should be able to help you as long as you did it directly after the thing happened. I cannot do it 2 weeks after because you received grade 0 and only now realized something went wrong. Now, it happens to even the best of us. I'm just saying, please make sure to double check. And if that happened to you, make sure to fix it. Okay. And again, for now, just remember, I am going to be dropping 2 lowest scores for homework/quizzes. This is like weekly assignments, and for discussions. So it's not the end of the world, even if you screwed up one quiz or like 2 quizzes. Okay, it shouldn't affect your grade badly. Okay, so those are a couple of like hint and administrative things. I also would remind you that we do have the test next Wednesday. I did email to everybody to in the announcements with the details of where the test is located. Please make sure to be there. There are not going to be makeups or anything for the test, so don't forget to put it on your calendar. And of course, I will be reminding it on Friday and Monday and next Wednesday, but still, just in case, because even though I'm reminding it all the time, generally, unfortunately, at the end, somebody does steal. forgets about it or does something stupid, and we do not want you to fail the class due to it, because the test is a lot of points, and it is important to be there and try it. Okay. Now, also in the announcement, I mentioned that I decided to change my mind on you a little bit for the best for you. So for the test, it is going to be a closed textbook, closed notes, paper and pencil as promised. However, I decided that I'm going to give each one of you an opportunity to bring one-sided A4 page with your notes. So whatever you write on this one piece of paper is going to be okay. So you can bring one piece of your own notes. Okay? And that's the only thing you're going to be able to use. So you can put there whatever you want, any formulas you want, any definitions you want, you know, all the directions. I think it's kind of going to be helpful because it's one piece of A4. A4 is a traditional print paper. So it's a traditional, you know, note side thing. It doesn't have to be handwritten. You can print it and it can be, you know, on the computers, but I can definitely tell you that the amount of things I can put in my own little handwriting is twice bigger than what I can type. Yeah, I do not know the exact size of the printer paper, but it is a traditional, like traditional notebook paper. Just like, okay, you can look at the paper you have for your discussion you're going to receive right now. Yes, one page, one side, like that. You can do whatever you want with it. Okay, great. Well, on that note, let's move on. So today on the discussion, you're going to be working more with the functions and writing proofs of the functions like one-to-one, onto, and so on. All of those things are important. They are going to come in a different places. So you really need to understand how functions work. And again, this class, it's not like I have like on the functions, you can spend like pre-calculus, correct? It's all about functions. You can spend semesters on it. But that's not the idea of the class we have out here. First of all, we do assume you know at least basics of what the function is already. And second of all, we kind of more focusing on how you really prove the things, like prove the properties of the functions, which is different from what you do in traditional like pre-calc, which probably most of you took already anyway. Okay. So last time we finished up section 2.3, which was talking about functions. We talked about one-to-one property. We talked about onto property. We talked about that in order to be bijection, a function should be one-to-one and onto. And only if a function is bijection, only then you can have an inverse function, and then you can find this inverse function. We specifically talked about how important it is to understand the range and domain of the function, because well, not sometimes, but always the property of one-to-one and onto really depends on your range and domain. And hopefully today during the discussion section, you'll have a chance to practice it all. So don't forget to ask questions of your TA if you have any. Okay, so the new topic for today is we are moving on to section, to section 2.4. And section 2.4 talks about sequences and summations. Okay. So first of all, let me define what a sequence is. A sequence is a function from a subset of set of integers to a set S. Generally, it is from set of 1, 2, move on, to A1, A2, and so on. Now, right now, what I drew here is we have a set of integers, we generate a sequence. So sequence is, the keywords for you is ordered. Okay. Now, we also defined every term to be an AI. It's term I in the sequence. Now, here is an example. I can say the sequence AN. So again, sequences are still going to be in curly parentheses. I can say the sequence is given using the rule AN is equal to N squared. So it's kind of like an f of x equal x squared to some extent, but a little bit differently, because now we're going to be not generating all possible real numbers, but we're only going to be looking pretty much at integers. And this is, you know, an important thing out here. So in this case, my terms are A1, A2, and move on. And then since I start with my indexing being 1, 2, 3, and so on, my very first term is going to be 1 squared, which is 1. My second term is going to be 2 squared, which is 4. What have I done? Okay, and then 2 squared, which is 4, and then 3 squared, 9, and 4 squared, 16, and 5 squared, 25, and I'm going to keep on going. So the big difference here between just traditional x square and the sequence is functions are generally continuous most of the times, meaning I can draw them using one line. So generally, when you have a function, you can draw it without taking your hand out. Okay, so you can kind of go like that. Now, the sequence is generally just set of dots. Okay, so actually, sequence is discrete. So if you ever wondered, what does it like? Why do we study discrete structure? What it means? Things you study in pre-calculus and calculus, it talks about continuous functions generally and continuity of a function, while the discrete structures are talking about sets and sequences and logic, things which are discrete, separated. So they're not continuous, they're kind of like a dots on a plane. Okay, this is a big kind of difference between those two subjects. So now let's talk about algebraic and geometric progressions. So an arithmetic progression or algebraic progression and let me define that. An arithmetic progression is a sequence AN of the form A plus D, A plus 2D, A plus 3D, keep on going. The general term is going to have F plus ND, and you can keep on going. Now, here is an example, which is also going to answer Pakshar question about negatives. An example is going to be AN equal to -8 plus 3n. This one, let's look at it. So when n is equal 1, my first element is going to be -5, agree? When a is 2, 3 multiplied 2 is 6, -8 plus 6 is -2. And then I'm going to have 1 and 4. And who's next? 7, yes. Keep on going. So first of all, do you really need to plug it in every single time, or do you see a pattern here? It's a +3, correct? From element to element. So pretty much, if you think about it, I start with -5, and then I add 3 ones, and then I add 2 threes, correct? Which is 6, correct? So the other way of looking at this type of pattern is I kind of always said plus the same amount to every next term. So I take the previous term and add the next one. Now let's do another another definition. So now let's talk about a geometric progression. Is a sequence of the form A multiply R, A multiply R square, A multiply R cubed, A to the power n for the general term, and you keep on going. So an example can be something like an equal to 3 multiply -1 to the power n. Now let's try and generate this sequence. What are we going to get? Well, when n is equal 1, -1 to the power 1 is -1. So I'm going to get -3. Then I'm going to have -1 to the power 2, correct? -1 to the power 2 is going to be +3. And then -3 again, and +3, and you keep on going forever. So what is my other keyword besides the keyword ordered for the sequence? Remember how I said we're going to be trying to remember. So when we talked about sets, we said that the sets must be unordered and distinct. Those were the two keywords we had. And distinct meant we cannot repeat same elements. Now, for the sequence, what are our keywords? What do you think? So one of them we said order. What is the other one? Yes, can. It's not even non-distinct, then they can repeat. Don't have to be. They can be distinct, but they don't have to be. So it's not like they must to be repeating. It's just saying sometimes they can repeat, that's fine. Sometimes they will not, but sometimes they might repeat. Okay, beautiful. And you can kind of see it over here, right? Yeah, so they're ordered, and it's not just not distinct. It's more of don't have to be distinct. They do not really have to repeat. Look at my sequence on top, algebraic one. Will they ever repeat? I have -5, -2, 1, 4, 7. I always said +3. Is it ever going to repeat? No. So they're all going to be distinct. But it doesn't have to be this way, because now if you look at my geometric expression, they can repeat. And both of them are sequences, correct? So both of them are sequences. So there is no really rule about being distinct. Okay? It's just can be distinct or not distinct. Either one is fine. Okay, great. So let's do another example. The other example is going to be an is equal to -4 like that. This is the same. Now, are all sequences infinite? This is a good question. So generally you have a rule saying generally sequence has a pattern which you can generally follow till infinity. However, sometimes we're going to say we're only interested in sequence from element 1 for indexing, kind of like from 1 till 5, for example. I'm not interested of what's coming after. So you can generally, the rule is infinite. It can work for any n, so it's kind of like an infinity type of a thing. But at the same time, we can also say, but we are going to be focusing on this range or on this portion of a sequence, and then the sequence is going to be finite. Does that make sense? So yes, so now we have this sequence over here I wrote down, which is a geometric sequence. The sequence on top, for those who already did Calc 2, you probably know, you have studied like some sequences and stuff, so you probably know this is an alternating sequence, correct? And you know about some of the properties of them. Alternating meaning it's changing sign every other term. But let's look at the second one. Does it always have to be a like geometric sequence progression? Does it always has to be alternating? The actual answer is no. So let's look at what we have. When I have 1, my value is going to be -4 divided by 2, which is -2. And then when my n is equal to, I'm going to have 4, -1 is going to be my answer. And then it's going to be -1/2, -1/4, and we will keep on going. And whoever wrote its convergence to 0, that's correct. It's going to become smaller and smaller and smaller and smaller and smaller, and it's going to try to reach 0, but it never will. So yes, but you do not need to know the properties. We are going to just play with some of it, and we are going to talk about how you can represent sequences in a different way, and then we're going to do some proof writing about sequencing at some point of time. So again, as I said, the discrete structure class is different from some of the other classes you took or studied. There are tons of things about mathematics and tons of things about properties. We are kind of focusing on how we argue why the things work, how we show things work, how we prove things wrong. So we study different structures and we study their properties and we show why those properties work. Okay. Where am I? Here we go. So now let's define recurrence relation. So a recurrence is an expression that represents an in terms of one or more of the previous terms. Okay, so we are going to do a little exercise right now. So generally, when we want to create a sequence, we give a rule on how to create it. So the previous rules you have seen, they were using n. So they were kind of having a function like an equal to something, and then I used n in here. So for example, 2 minus 3. Well, actually, let's do 2 minus 5n, okay? For example. So in this case, an uses n. So by plugging in numbers, I can easily tell you what any term is. So can you compute for me A10? What is A10? Okay, I have some people saying negative 48, and I'm going to trust you. I'm not doing the math myself. How did you do it? Well, you do plug in 10 instead of n, correct? And you do the mathematical computations, which are not horrific in this case. Now, this is different from the recurrence relation. If you think about it, if I'm going to now start writing things like, what is my sequence starting from 1? So when I plug in 1, I'm going to get negative 3, correct? And then when I plug in 2, I'll get negative 8, correct? And then when I plug in 3, I will get negative 13. What is my pattern here? It is subtracting 5 every time, correct? So negative 18 and so on. Now, if I'm going to keep on going, I can get to the negative 48, correct? Just doing negative 5, negative 5, negative 5. I can do it, this term. But some people are saying, okay, let's write it in a in a real language. What we do is we do negative 5 from previous term. Correct? That's what we're doing. So the way to write it is to say an is equal to an minus 1 minus the value 5. Now in here, n minus 1 is my index, correct? Now what I have here, this is the recurrence relation. I gave you a recursive way of how to do it using previous terms. Now, how many sequences are going to be able to use formula an equal to an minus 1 minus 5? Actually, I can generate infinitely many different sequences for you. Why? Because in this case, I can start at the different positions. So in order to use it, I need to know what is my A1, correct, or A0. And I can put whatever I want out there. And depending on what I want out there, I'm going to get different results. So if I'm going to put -3 here, yes, the sequence I am going to get is -3, and then -8, and then -18. So right now, this is equivalent to that and kind of equivalent to that, different representation of the same sequence. However, if I'm going to change my mind and I'm going to say my A1 is equal 0 and my AN equal to AN minus 1 minus 5. Now let's try and generate it. What are we going to generate? So our very first term is going to be 0, correct? My second term is going to be 0 minus 5, which is -5. And now minus 5 again. And again. And keep on going. So the fact is, when you have recurrence relation, not only you're supposed to have a general formula using the previous terms, but you also need to have a basic case, the starting condition, the point of where the sequence starts. Now, depending on how many previous terms you use, you might either need just one, like A1, or you might need to have multiples. So let me show you another example. So let my AN to be 2 AN minus 1 plus 4, and my A0 is going to be 3. This is the recurrence formula, and this is initial condition. Now, beforehand, I was starting with 1, but as I said, you do not have to start with 1. I said generally we start with 1, but sometimes we prefer to start with 0. So in this case, my first element is still 3. My second element is going to be 2 multiply 3, which is 6 plus 4, which is 10, correct? So we generated as the first one is 3, then 10, then 24, then 32, and keep going. Question. Can you find A10 for me? Yes, no? It doesn't mean you're finding it for me right now. I just need to understand, can we find it or not? Can you find me A10? Yes. Is it going to be easy? What do I need to know in order to find the A10? So first I need to calculate A9, correct? But the fact is, in order to calculate A9, I need to calculate 8, correct? And so on and so on. So now let's discuss it. So using this formula, was it easy to find 800? Using a formula like that. If I want using the formula on the screen, is it easy for me to find A of 100? Using this formula, for example. Yes, we just plug it in, correct? Is it easy using this formula? No. So why the heck do we need both ways? It seems like the other one is better, isn't it? And now let's think about it. Was it better? Now, when you did this sequence and I need next element out here, what do you prefer? To plug in a number and do the calculation? Or are you going for the finding next term? Or are you just going to multiply it by half pretty much? Which one is easy? Multiply it by half using this term. Multiply -1/4 by half, or plug in into this formula, calculate 2 to the power 5, and then do the computations. Which ones do you prefer? Probably simple one multiply is easier, correct? So this is why there are different ways of representing the same sequence. Sometimes it's easier to use the recursive formula, especially in programming, because it doesn't require a lot of mathematical computations. However, in other cases, it's easier if you, for example, want to find A of 100 to use another form. So what I'm trying to say is both forms are useful and has their advantages and disadvantages. Okay, great. Now let's do one more example. My AN is going to be equal to AN minus 2 minus 2AN minus 1. This formula is iterative or recursive? Recursive. The iterative formula is the one which just uses n. It doesn't use previous terms. So every time you see previous terms, it's a recursive. Every time I have a recursive formula, I also need to have what? Just the formula, not enough to construct it. What else do I need to provide to you? Initial conditions, correct. How many initial conditions do I need in this case? Yes, so in this case, we need to know 2 consecutive terms. So I'm going to tell you A0 is -1 and A1 is 5. Can you calculate A2 for me? How much is A2? It's -1 because A0 is going to be -1 minus 2 multiply 5, which is -11, correct? And now I'm going to calculate A3 for you. So in this case, I can use those 2 terms, correct? So now I'm going to be using 5 minus 2 multiply -11, which is going to be 22, 27. And you can keep on going. Okay? Great. So next, Now we're going to talk about, well, actually, I'm going to switch microphone for a second. And you're going to watch that video. Can you hear it? Okay. Stop. Oh, let's try it like that. What about now? We will make it work.
The sequence begins with the numbers 1, 1, 2, 3, 5, 8, 13, 21, 34, and continues indefinitely. Each number is obtained by adding the last two digits together. If we were to take a perfect or golden rectangle, break it down into smaller squares based on Fibonacci's sequence, and divide each with an arc, the patterns begin to take shape. The sequence begins with the numbers 1, 1, 2, 3, 5, 8, 13, 21, 34, and continues indefinitely. Each number is obtained by adding the last two digits together. If we were to take a perfect or golden rectangle, break it down into smaller squares based on Fibonacci's sequence, and divide each with an arc, the patterns begin to take shape. We begin to see Fibonacci's spiral. The spiral in and of itself is insignificant. Its importance is revealed in where we find it. Take, for example, the sunflower. The display of its florets are in perfect spirals of 55, 34, and 21. The sequence of Fibonacci. The fruitlets of the pineapple create the same spiral based on the sequence. The pine cone does the same. As currents move through the ocean and the tide rolls onto the shore, the waves that bring in the tide curve into a spiral that can be mathematically diagrammed onto a plot at the points 1, 1, 2, 3, 5, 8, 13, 21, 34, and 55. Buds on trees, sand dollars, starfish, petals on flowers, and especially the nautilus shell are formed with this exact same blueprint. With each segment of growth, the nautilus adds to itself one more value on Fibonacci's scale. This blueprint can be seen around us on a small scale every day, but the greatest example of all is directly above our heads. At an average of 100,000 light years across, even the spiral of the galaxies above us are formed with the exact design that the tiny shell is formed. This sequence or blueprint appears to be the trademark.
Okay. Okay. So hopefully you were able to hear it, kinda. If not, you have a link in the chat. I know somebody is now actually spamming the chat. Don't do it. Let's keep it for the class, please. So pretty much, what did you learn from this little movie? What the movie is talking about? And how it is connected to what we are studying right now. Yeah, so pretty much it talks about a very special sequence, which called Fibonacci sequence. Fibonacci sequence uses an extremely easy pattern. It has F0 equal to 0, F1 equal to 1, and then the formula for it is f of n is equal to f of n minus 1 plus f of n minus 2. So what it really does is it adds two previous numbers and it creates a sequence. So 0, 1, 1, 2, 3, 5, 8, 13, and keep on going. So you just add two previous things. What it also talks about that although it's just it's a simple sequence, correct? It's not too complicated of a sequence, and it's add just two numbers together. But the fact is it's pretty significant because we can see the Fibonacci sequence in nature and a lot, and it helps us to calculate some of the properties of waves, for example. It's a cool sequence, and it has a real life example, which is as perfect as it gets for the mathematics. So now you do need to understand how the Fibonacci sequence works and to be able to calculate the Fibonacci sequence elements. Now, what type of formula Fibonacci sequences uses? Is it an iterative formula or recursive formula? It is a recursive formula. Okay, good. So I had a question out there. Do we have to start with 0 and 1? Well, we don't. Another way to say is F1 is equal 1 and F2 is equal 1. And then I can generate 1, 1, 2, 3, 5, 13. So it kind of depends who you ask. Sometimes we started with 1, 1. Sometimes we started with 0, 1. At the end, it's the same Fibonacci sequence. And the indexing in this case, it's not too horrifically differently. So it's the same sequence. No, you cannot start Fibonacci sequence with 3 and 4 because it's not going to be a Fibonacci. Fibonacci is a specific, Fibonacci has a specific starting condition. So it's always like 0, 1, 1 or 1, 1 and so on. Okay, on that note, we are done for today. And you don't forget about discussion. Don't forget about joining the discussion group. I'm going to see you all on Friday. Have a good day. If you didn't have a chance to hear the video, watch it. It's a good one.